lecture in Engineering Maths 5 in the last lecture of the year, so hopefully you'll never have to see me again. And we are going to be looking at double integration but we're going to be using polar coordinates. Okay, so when we want to integrate over disk-shaped regions, it is much easier to convert x and y to r and theta. I don't have a theta button on this, so I'm just going to put a theta in here like that. Okay, so when we want to integrate over disk-shaped regions, it's much easier to convert x and y to r and theta. Now, remember, these are our two formulas for polar coordinates. X is equal to r cos theta, and y is equal to r sine theta. Okay, and remember, if we've got x and y, our coordinates normally, if that was 2 along and 4 up, that would be the coordinate 4, 2. But remember, what polar coordinates does is it measures the length of the line out, and it measures the angle in here that it goes through. Okay, so that's r, and the angle it goes through is theta, and that's how polar coordinates work. Right, so if that's your point there, that point there, and rectangular or normal form, if that's 4 along, let's say 5 up, that coordinate there in normal rectangular coordinates would be 4, 5, right? But we know how to work that out in polar form. We use r and we use theta to tell us what the coordinate is in polar coordinates. Right, so what happens in our polar coordinates is, if we have the double integration over the region R, and that's what we've been looking at just so far, and we've been looking at xy dA, right? Or we could have dx dy there, right? Means the same thing. So it doesn't matter what you choose to use. I'll just use dx dy, but I'm just showing you they mean the same thing, right? dA just means it's either dx dy or dy dx. I'm doing the same thing. Right, now, what happens when we go into polar form for this is that rather than x, we've got r cos theta, and rather than y, we've got r sine theta. Now, what also happens is, and again, I know I've said this a few times in the last few lectures, I don't have enough time to go through it in this course, but if you look online, there's an extra factor of r dr d theta, right? So that extra r that you've got to put in to multiply everything by, don't forget that when you end up converting to polar coordinates or polar form. Right, now the key thing is our region. Now, our region is normally described by a rectangle or the area between two curves and all that kind of stuff. We've done that so far. But our region this time is going to look like a circle, right? It's going to be disc shaped because it's much easier to deal with circles and disc shapes. So basically it's going to be easier for us to find the volume of cylinders and all these kind of shapes that would involve a circle. Right? You might say the volume of a cylinder is dead easy. I know, but it could be a cylinder which has got a sphere on top of it for a roof and all this kind of stuff, right? Right, so now I'm going to say that our limits are r equals a to r equals b. Right, now that matches our r. Now in polar coordinates we always integrate with respect to r first if we can. Right, pretty much every time. I can't think of any time when we wouldn't integrate with respect to r first. Right, and then theta we say is between c and d. Right, now I like putting the letter next to the limit here, as you've seen through the rest of double integration. It just makes it easier when you've got to substitute it in. Right, let's keep going. So, now, a couple of things. The limits r equals and r equals b are the radii, or radiuses, we would say radii in maths, of our internal and external discs. Right, and I'll show you exactly what that means. It's going to be obvious when it's a diagram. Right, and theta is equal to c, and is the start and end of the angle our disk is moving through. I left a wee gap there so I can put thetas in because I can't be bothered finding the theta button on the computer, so that's theta equals C. Right? Right. Now, one thing to note, and this is really important, right, really, really important. Don't forget this. Particularly important for your assignment. Trig identities. So these are on your formula sheet. Are really important when using polar coordinates. I'll just do a wee IE. For example, it is impossible, or pretty much impossible. I'll just need to write and stuff. If I end up at any point with either sine squared theta or cos squared theta or cos theta sine theta or sine theta cos theta, I can't integrate those like that. I must use the trig identity for each of those. So I've got to change that to using a trig identity. I'm not going to write that down here because you should know what it is. It's on the formula sheet. And I'm going to include it in the examples anyway, right? So I just want to, I'm going to change that using a trig identity. Right. Now, what I'm going to do first is just show you from a diagram how we get our limits. And then I'm going to do a full question, right? So this is just choosing our limits. But I'm not going to actually do any integration here, right? So if I've got this region here, and I'm gonna sketch it, right? If I've got this region here, right? Now, I'm quite lucky with this software that I can make circles quite easily, because you know from my drawing in college, I can't draw to save myself. Right. Okay. So let's say I'm given a region. This is my x-axis. This is my y-axis. Now, I know from polar coordinates that that's 0, or using radians, that's pi by 2, that's pi, that's 3 pi by 2, and that's 2 pi. Or sometimes we think of that as negative pi by 2, and 0 again. Depends on what we're doing. I'm just going to use between 0 and 2 pi for my polar coordinates here. I know a lot of the time when we're doing rectangular to polar, we've been going between negative pi and pi. I'm just going to use 0 to 2 pi. It doesn't make a difference. That's what I'm going to do here, right? So let's say this is my region. Let's say this circle here, and this coordinate point here is 3, right? This coordinate here is 7, right? So that coordinate there is 3, that coordinate there is 7, right? And let's say this here is the region I'm looking to integrate about. Okay, so that means the rest of this shape isn't here, right? So none of this shape is actually here. Right. So this is the shape I'm effectively integrating over. Right, so it's 2 discs, right? One with radius 3, that'll be negative 3. One with radius 7, so that'll be negative 7. And I wanted it, and it's this region here, right? Now, that's 0, that's pi by 2, that's pi, that's 3 pi by 2, and that's 2 pi, right? That's how these things work. So here I had 2 discs. One with radius. Remember, radius is from the centre to the outside, so that's 3, not negative 3. And one with radius 7, right? But I didn't want the whole disc, right? Because the whole disc would be the thing all the way around. I only want the disc, this little section here. So just now my limits would be for the whole disc. Now my region, or my angle that I'm going through, starts here, is this angle here, right? And that angle starts at pi by 2 and goes round to pi. So my angle theta and goes to pi. So I would write out my double integral. And remember, I'm going to polar coordinates. So it becomes r cos theta, r sin theta. Remember your extra factor of r dr d theta. Right? Now, the internal limits are the radiuses of your disc, or the radii of the circle that make up the disc. So the bottom one has radius 3, the top one has radius 7. So that's me created that disc, right? And the angle starts at pi by 2 and finishes at pi, right? So that's r equals 7, r equals 3, theta equals pi, and theta equals pi by 2. I don't like the way that looks, we'll change that pi by 2. Okay? Let's get let me show another one, right? Okay. Let's say the question gives me this and says, right, this is your region of integration here. So I only care about that little segment of the circle. The rest of this doesn't matter, right? It's only this segment that I care about, right? So there's my x, there's my y. Right, and I'm going to tell you the radius of that circle is 8. Now, in polar coordinates, that is 0, pi by 2, pi, 3 pi by 2, and then that would take you back to 2 pi, so we can just keep that as 0. It means the same thing. Right, so what I've got is, I've got one disk with the radius 8, right? And all the question's looking for me to do is integrate over this region here. So the rest of that I know it's a different colour of yellow. This is high tech as I go, as you know, right? So the actual region that I'm looking to integrate is just this little bit here. But you've got to draw the full disk so that you get the initial circle so you can see what's going on. Right, now my angle theta starts at 0. Okay, starts at 0 here and swings its way around to pi by 2. Right, so our double integral we would set up like this. So our function is going to look like function r cos theta, r sin theta, r dr d theta. Now that's the way it looks. Right, so my internal integral always is to do with the disk. Now I know that I've only got one disk. Now if you've got one disk, that means it's a tiny little circle in there with radius 0. Right? So really you're going from 0, because a wee tiny origin spot with radius 0 in there, and you're going to 8. So if you've got two circles that make up your disk, you're going to have a number in here. If you get one circle that makes up your disk, you're going to have a 0 down here. And it starts at 0, so I'll just put r in. I always forget my r's. R equals 0, then r equals 8, and theta starts at 0 this time, because that's where my region starts, and it goes all the way around to pi by 2. So that is my limits for my integration. Right? So I just wanted to talk through how you get those limits. Right, so let's do a proper example now. Okay, example 1. Now, the region of integration can either be given to you as a picture or it can be given to you as a description. Now, in this course, I'm going to give you a picture, right? But in real life, it's more likely that it's a description, because it'll be a description that you're working with. Right, so we want to integrate over this region R 2xy dx dy. Right, now I'm going to give you the region. The region looks like this. It's got a circle. Second circle, right? Right, so I'm going to say, let's label my axis, right? That's x, that's y, right? I'm going to say this is In fact, I'll make this wee circle a wee bit smaller. If I can, I've got a pen. I want to make it look a bit right. Right, let's do that. Okay, that looks a bit better. Right, so what I'm going to say is I want this region here. So this bit shaded. Can you always measure anti-clockwise with your angles? By the way, I didn't say that earlier. Always measure anti-clockwise, right? Now I'm going to tell you that the radius, that coordinate there is 2, and this coordinate out there is 5. Even if it doesn't look like it, right? So 2 and 5, right? I want the integration to happen. Okay. So let's set up our integration. This is a full question. That's all you're going to get. An integral with your function in here and the region you've got to integrate over. So let's do my limits first. So remember it becomes r dr d theta. dx, dy or dA always becomes these three terms here when we're changing to polar coordinates. Okay, every time. Now, your radiuses, so the smaller radius or radii is 2, and your outer radii or radius is 5. Right. Now, we know that this is 0, pi by 2, pi, 3 pi by 2, 2 pi. Now, I'm not interested in the rest of this disk, that doesn't matter. I'm only interested in this shape here. Right? So, I'm going from theta equals 0, anti-clockwise through to theta equals pi by 2. Right, so I've set up my limits. I've put in my r d theta. Now, I need to swap my x and y. Right? Now, so that's going to be 2. Now, x is r cos theta, and y is r sine theta. Right? Remember I said that in the first note. So we always swap your dx dy for r dr d theta, your x for r cos theta, and your y for r sine theta. So let's simplify this down. Now, I know it looks difficult. There's nothing really difficult about this. The difficult thing is going to come with a wee trig identity thing that I spoke about earlier. But apart from that, it's going to be quite easy. Right, and I'm not expecting you to leave as much of a gap between your integral signs. That's only because I'm using this rubbish graphics thing that I've spoken about before. Right, so 2 times r times r times r, so that's 2r cubed cos theta sine theta dr d theta. Right, so first thing I've got to do is integrate this with respect to r. And remember, if you integrate something with respect to r, you only integrate this bit stays the same, right? Because you treat thetas as a constant, right? So I've got the integral between theta equals 0, theta equals pi by 2. Remember, we're changing to square brackets. That gives me 2r to the power of 4 over 4 cos theta sine theta between 2 and 5 d theta. Right, let's remember this is r equals 5 and r equals 2. So we're going to substitute, in fact I'm going to simplify it first before I do anything else, because these can get a wee bit horrible if we don't simplify them as we go. So that's r to the power of 4 over 2 cos theta sine theta r equals 2, r equals 5, d theta. And please try and simplify it as you go. I know I've got an awful habit of sometimes not doing it. It doesn't actually make a difference because you're going to get a numerical answer at the end, so it doesn't really matter when you choose to simplify. Right. So we're going to substitute in that. So that's 5 to the power of 4 over 2 cos theta sine theta, take away 2 to the power of 4 over 2 cos theta sine theta d theta. Right, so let's type this into a calculator and see what happens. I suppose you should have equal signs all the way down. Telling a story, haven't I? Right, so right, so 5 to the power of 4, I've got my calculator here. Right, 5 to the power of 4 divided by 2 is 625 over 2. We've got 625 over 2 cos theta sine theta. Fair enough. Take away 2 to the power of 4 is 16. So 16 over 2, which is just 8 cos theta sine theta d theta. Right. These are just the same thing, so I'm just going to take them away. So 625 over 2, take away 8, or take away 16 over 2, whatever you want to think that. Right, so that gives me 609 over 2 cos theta sine theta d theta. Right. Now, to make this a wee bit easier, I'm just going to take that constant number that's multiplying everything out before the integral sign. Could have done that with the 2 at the start of the question, but I didn't. Oh. Right, now, I don't know how to integrate cos theta sine theta, but if you notice what I said earlier, cos theta sine theta is one of these terms that I can only integrate using a trig identity. So, let's go find out what that identity is. So, this is your formula sheet that you get at the start of every engineering assignment or assessment that we've done throughout the course of this year. Right, so up the top here, we've got these trigonometric formulas, right? So if I got sine squared and I wanted to integrate it, I would use that one there. If I had cos squared and I wanted to integrate it, I'd substitute in that one there. Now, I have sine times cos or cos times sine. So that means I need to use this one here. So there's going to be a little bit of manipulation, right? So let's see what happens. Oh, right. So it tells me in that sheet that sine 2 theta equals sine theta 2 sine theta. Let me just change it. 2 sine theta cos theta. Right, I've got cos theta sine theta, that's the same thing, but there's this 2 that's in the way. So that means I need to take a half. So if a half sine 2 theta is going to be sine theta cos theta. So I'm going to substitute this thing here in place of that there. because this is my trig identity bit. And your trig identity in your assignment is going to be trig identities twice. So make sure you pay attention, right? It's going to be either a sine squared, a cos squared, or a cos multiplied by a sine, and you're going to have to get the trig identities from that sheet. So I'm just going to put a wee line there, because this is a wee bit that we've done separately. Right, so that is equal to 609 over 2, the integral between theta equals 0 and theta equals pi by 2 of a half sine 2 theta d theta. Now, I can integrate sine 2 theta d theta, it's a doddle, but I'm just going to move that half outside in the same way that I did before. Right, so 609, right, so I'm moving that half out, so I just move it out and it multiplies. So 609 times 1 is 609, 2 times 2 is 4. Sine 2 theta d theta. Right, now we just integrate that. Integrate sine 2 theta is dead easy. So I'm integrating so it becomes a square bracket, like that. And that becomes, well, sine, if you integrate it, becomes negative cos 2 theta, and you divide by the 2 between theta equals 0 and theta equals pi by 2. Right, so let's substitute in our limits. So we get 609 over 4 multiplied by negative cos 2 times pi by 2 over 2, take away negative cos 2 times 0 over 2, and remember that 609 over 4 is multiplying everything in there. So remember your calculator needs to be in radians, so negative cos pi divided by 2 is a half. Yep. Take away negative cos 0 divided by 2 is negative half, so that's take away negative a half, like that. So that adds together, so our final answer is 609 over 4. Those two together, a half plus a half is 1 units cubed, because it's a volume I've worked out. So I've been able to work out that the volume between the function z equals 2xy and this disk here, the volume between those two things is 609.4 units cubed. Right, there we go. Next one. Now this next one, a wee bit more tricky, but it should be the same kind of thing. Right, now this is example 2, and this is question 2 from the revision booklet. Right, so we're wanting to integrate over this region R 2xy over x squared plus y squared, and I'm just going to call it dA, because remember dA just means dx dy or dy dx, it doesn't matter, right? The question can just say dA for you, right? And then the question is going to give us your region of integration, right? Now, I'm going to say I'm going to freehand draw it, but that would be a disaster, right? Okay. So, I'll give you a diagram. I will tell you that this is X and Y, and right, that's 3, and that's 5, right? But the actual region is this tiny little region in here, right? And it's going to tell you that this bit here, where the region starts, is 3 pi by 4, right? So I'm not interested in any of the rest of this disk. All I'm interested in is this little tiny section of disk here, right? That's my region of integration. The disks are just there to give me the correct shape. Okay, so this is the way the question would be given. Let's set up our integration. So it's going to be 2. In fact, no, it's not. I'll just save that. I'll just do the limits first. So do the limits first. So dA always becomes r dr d theta. Remember that r is important to us. Now, our disks are 3 and 5. The radius is 3 and 5. Those are never negative, right? Because it's a disk. A radius can't be negative. So that's r equals 3 to r equals 5, right? And the angle, remember we always measure counterclockwise or anti-clockwise. So our angle starts here and moves round to here, right? So our angle starting at 3 pi by 4 and it's finishing at pi. So now set up my limits. Now this is where things get a wee bit complicated now. Remember, every x you swap for r cos theta. Every y you swap for r sine theta. And the same thing, so that's going to be r cos theta squared plus r sine theta squared. R dr d theta. So, same steps as always. You swap your dA or your dx dy for r dr d theta. You swap your x's for r cos theta and your y's for r sine theta. And then we're going to see if it simplifies into something nice. It should normally become quite a nice function. Because that just now is impossible to integrate. Right. Theta equals 3 pi by 4. So I'm just doing this exactly the same way as you would do it in an exam, if this is your exam question. Right, so that top bit gives me 2r squared cos theta sine theta. Oh, you've got this r here as well. So that's going to be, because remember, anything that looks like it's in the middle really is on the top alongside everything else. So that's 2r cos theta times r sine theta times this r here. So that's really r cubed in there, isn't it? Okay, and I did that deliberately. It's not a mistake, just to try and highlight where a mistake would be made in this question. Right, now I need to square the r and square the cos. So that's going to be r squared cos theta plus, sorry, r squared cos squared theta plus r squared sine squared theta dr d theta. Now look, that r is gone because I've absorbed that into the top line of my function. Right, now, two things. I know I can't use this. I know I can't use that. I know I can't integrate cos squared. I know I can't integrate sine squared. And I know I can't integrate cos theta sine theta. right? Impossible. So I'm going to do the exact same thing as I did before, right? So 5, I think it was 5, yeah. Right, so this bit here, exact same thing as before. Cos theta times sine theta becomes a half sine 2 theta. Right, remember that's from the previous slide, because remember it's sine 2 theta equals 2 cos theta sine theta. But I don't have two of them, I've got one of them, so I divide it by 2 to give me the half. Right, so that's the trig identity I've used on the top. Right, now one thing I know is, and let's have a wee look if it's on my formula sheet, is that sine squared plus cos squared equals 1. I should say A in there. Anyway, that formula sheet's wrong. So if I take out that r squared as a common factor, that means I've got cos squared theta plus sine squared theta. I've still got dr d theta, right? But I know that cos squared plus sine squared theta equals 1. It's the other trig identity from my formula sheet. So that means I can swap 1 in place of all of this stuff here. So that's going to give me 2 times, so that's going to give me r cubed sine 2 theta, because if I multiply the 2.5 together, they go away, right? And cos squared theta plus sine squared theta, well, that's going to give me 1, so that's just r squared I've got on the bottom, dr d theta. Okay, so now it's looking a lot better. So the last thing that I can do is r cubed divided by r squared is just r. So it's just the integral of r sine 2 theta dr d theta. Okay, now I know in the question I've split it up into 2 or 3 sections in the actual revision sheet, but I'm just showing you that if we're given this as just a straightforward question, this is what you would do. Right, so first thing I'm going to do is I'm going to integrate. That's something I can integrate quite easily. So you integrate your r's first, and then you're going to integrate your thetas. So let's integrate our r's to start off with. So I'm going to integrate the r, and that bit's just got a theta, so that's going to stay the same. So that's r squared over 2 sine 2 theta between r equals 3 and r equals 5 d theta. Right, so let's substitute in our limits. Of 5 squared over 2 sine 2 theta, take away 3 squared over 2 sine 2 theta d theta. That theta looks like a 6. Anyway, right, so type that into your calculator. So that's going to be that's going to be 25 over 2 sine 2 theta, take away, what is that, 9 over 2 sine 2 theta, theta, that just simplifies. That's 16 over, so that's 8 sine 2 theta d theta. 25 take away 9 is 16. 16 over 2 gives you your 8. And just type that into the calculator. It'll do it for you. There's no need to do it in your head. Right, 8 sine 2 theta. So when you integrate sine, it becomes cos. That's going to be 8 cos 2 theta divided by 2 between theta equals 3 pi by 4 and theta equals pi. So let's substitute in our limits there. So that is going to be 8 cos 2 pi over 2, take away 8 cos 2 3 pi by 4 over 2. So 8 cos 2 pi is 8, as you'd expect. Because you've got to remember that's just the same as cos 0 or cos at 360 if you're thinking of degrees. So that's 8 over 2, so that's 4 in fact. So that would give you 8 divided by 2 would be 4 right here. Cos, and again I'm just checking the calculator because it's been a long time. And that bit there just gives me 0 over 2, which is 0. So my final answer is 4 units cubed. So the volume between this function here and this part of the disk is 4 units cubed. Isn't that lovely? I'll do one more, why not? Right, last one. Example 3. So integrate over a region R, x, y, dA. And let's have a look at our region. Our region is going to be, oops, that is horrendous. Y and x, and that's 1 and 5, right? Now, see if you wanted to do the whole disk, you would use 0 to 2 pi, and that would give you the whole disk. This is a wee heads up if you wanted to integrate over a whole disk rather than just part of a disk. But anyway, I'm going to go, we'll just do this wee region in here, right? Really straightforward, right? So that's 0, and that's 2 pi. Or sorry, pi over 2. Sorry. Right. So let's set up our limits. So dA becomes r dr d theta. Remember that function of r Sometimes it makes everything a lot easier, so don't forget to put it in. And your limits, well, your radius of your smaller one is 1. The radius of your larger circle is 5. So that's your inner bound, that's your outer bound. And the angle it's going through anti-clockwise is from 0 to pi by 2. And x becomes our cos theta, and y becomes our sin theta. So I think this is very similar to that example we did at the start. But anyway, right, so that's going to be r cubed cos theta sin theta dr d theta. Right, same thing though, a spot that I've got a cos and a sine next to each other like that, multiplying. So rather, before I integrate my r's, I could integrate the r section just now if I wanted, but I'm not going to. I'm going to use a trig identity. And a trig identity from my sheet is that sine 2 theta is 2 cos theta sine theta. But I don't want 2 cos theta sine theta, I want one of them. So that's going to be a half sine 2 theta. So that means I can swap that, but for here. Right, because you should never have sine squared, you should never have cos squared, and you should never have cos times sine or sine times cos. If you've got one of those, it's trig identity time. Right. Right, so it's, I'll just put the thing in before I actually integrate. So that's going to be r cubed over 2 sine squared, sine 2 theta, not sine squared, sine 2 theta, dr d theta. Right, let's integrate. So that's r to the power of 4 over 2 times 4 sine 2 theta between r equals 1, r equals 5 d theta. Right, so that's going to give me uh, 5 to the power of 4, I'll change it to circle curly brackets, hold on. So I just substitute in the 5, that gives me 5 to the power of 4 over 8 sine 2 theta. I know I've missed out a step, but 1 to the power of 4 over 8 sine 2 theta d theta. And if I do that, I'll just miss out a step. If I evaluate that and take away that, it gives me 78 sine 2 theta d theta. Right, time to integrate again with respect to theta this time. So that's going to become 78 negative 78 cos 2 theta over 2 Lovely, they're both even numbers. Theta equals 0, theta equals pi by 2. So that's going to give me, I'll simplify it before I chuck in those limits. Remember your calculators in radians throughout this whole process. Every single question in engineering 5, calculator is in radians. Same should have been for engineering 4 as well. Right, so that's going to be negative 36 times cos pi. Take away negative 36, which is 72 units cubed. Right, now what I'd advise you to do is do the questions on the revision sheet for double integration over these regions rather than trying to do any of the ones from the actual booklet. The ones from the booklet are alright, but they get quite difficult. There's a lot of trig identities to do. So the ones in the revision booklet are good because you can go and look at my answers. So I think I put the revision booklet for Engineering 5 already up. I'll put the answers up as well if I haven't done already. If you get any questions, please let me know.